Hello everyone and welcome to another lecture. Today we want to discuss about logarithmic function and its multivaluedness, and also we want to see how we can find the branch points and the branch cuts for a logarithmic function. So recall from your previous lectures that if you have a complex number z and a log function was defined something like this, it turned out to be natural logarithm of r, and you had some I over here, you had your principal argument and a 2 pi n, and as you can already guess, the multivaluedness of a logarithmic function will come from this guy, this 2 pi n over here. So let's try to see an explicit example first. Let's try to evaluate what is log of I. If you draw the Argand diagram, you can see I is over here. It has a principal value of the argument as pi by 2, so this r will be just 1, so you will have ln of 1, and you have your I over here, pi by 2 over here, and finally the 2 pi n thing. So this will go to 0. You can see that now you have I pi by 2 plus 2 pi I n. Now let's take n equals to 1, and if you take n equals to 1, okay, let me just write it over here, it's pi by 2 times I plus 2 pi, and this will be 5 pi by 2 and I over here. But if you take n equals to 0, that is, if you take n equals to 0, log of I will be just I pi by 2. So as you can see, these two values are not equal, and this again reflects or mimics the fact that this log function is actually multivalued function. For even if you for in the z plane, that is, if this is your z plane, and if you rotate once and you come back to I, that is, for this example over here, you are, after one complete circuit, you are back to the original point on z. But you can see that in the w plane, or the value of the function, that is log z over here, it's not coming back to its original value, rather it's giving us a different value. So n equals to 0 means no circuit or no rotation at all. N equals to 1 means one complete circuit, n equals to 2 means two complete circuits, n equals to minus 1 would mean a one complete circuit but in the counterclockwise rotation. And you can even take that is n equals to minus 1, and you can see that log of I will be I pi by 2 minus 2 pi, and this is just minus I 3 pi by 2. And since the multivaluedness of logarithmic function is clear, and again we can see that if we rotate around or complete a full circuit around 0, we are getting multivaluedness of this logarithmic function, we can safely say that this 0 point is a branch point of our logarithmic function. So let's write that down. So z is equals to 0 is a branch point for log z. Similarly, you can think of z is equals to infinity is also a branch point for this logarithmic z function, that is log of z. And what we did in our earlier examples, that is when we dealt with the square root over z, we connected two branch points to make a branch cut. So let's try to do that here. So again, this will be our plane, and let's mark these branch points. Let's say this is infinity, though it is not, because infinity extends out, and this is our branch cut. Similarly, we could have taken the branch cut over here, over here, over here, and so on. And if you recall, the principal branch corresponded to n equals to 0. this corresponded to n equals to 0. So you can easily see that this red line over here, this is our principal branch. And to make the function single valued, we can stay anywhere within this branch. That is, if you, let me just use another color to show you that, let's say if you start from here, you are actually starting from the real line, and you can rotate, but you should stop at here. That is, you cannot cross this line. It should be a bit over here, and this will impose the condition, that is the theta appearing, that is the small theta, not the capital theta or the principal argument. So this is not the principal argument, so let's denote it by this. So this whole thing will impose this theta into a value of this, into a restriction like this. This is a strict restriction. To prevent the function getting multi-valued. And even an interesting feature of this logarithmic function is that, as you can see, if you increase n, this thing will increase, because pi of every time you complete a circuit around 0, you are adding a 2 pi to the pi by 2. That is for this example over here. So as a result, what is happening is that this value of log I is increasing only. And similarly, if you just do the rotation in the opposite way, it will decrease. It will increase on the negative side, or so to say decrease. So you can intuitively guess that no matter how many complete circuits you do, you are not returning to the original value that was for n equals to 0, right? So we say that log z's for log z function, that is, this is our function, the order for the branch is infinity. So what does this mean, that this order of this branch is infinity? From the perspective of geometry and topology, what is happening here is that whenever you are crossing this branch cut, you are not in this surface anymore. Rather than you are creating another replica of this whole surface, and you are over here. And these are called Riemann sheets. So for this logarithmic function, you will have infinite amount of Riemann sheets, and these branch points will be at the very adjoint. That is, you can take these two sheets and you try to join them, and this is where those branch cuts will lie. And this is like a teleportation thing, like you are over this surface. Let's call this, distinguish this by 1 and the dashed one as 2. So whenever you are crossing this branch cut, you are actually not in the surface 1 anymore, rather you are in the surface 2, and so on and so forth. But this is a discussion for geometry and topology, so let's not do this here. So this is how you can identify the branch point of a logarithmic function easily. And after you identify the branch point and you can draw the branch cut, then you can do the analysis that you want, and you will have a single valued function. Because I can remember that if you take this red line as your branch cut, you can just rotate around over here like this, or over here, and the function will be single valued. Because this theta, it will, let's say you start from theta is equals to, I don't know, 20, some value, let's not care about the units anymore. So as you rotate over here, this theta will go up to some maximum at some point over here. So this might be the maximum, and then it will just decrease again, and you are back to the same point in the z plane and also in the w plane as well. So there is no multi-valuedness, and your analyticity is also restored, and there is no ambiguity of derivative as well. So we are saved from each and every side. In fact, the thing that this 2 pi n is actually causing the multi-valuedness can also be seen as writing log of z as u plus iv, where u and v are function of x and y. I'm not writing them explicitly, and if you just write it as ln r times 2 pi I n plus I theta. This is our principal argument, remember that. So u will be just ln of r and v will be I theta principal plus 2 pi n. So this guy over here, this is a single valued function. And also r is always greater than 0. Sorry, greater than 0. This is another thing to notice, that this means just deleting the point r when r is greater than 0, because if r is 0, that means the point itself is z is equals to 0. And so if you delete it, then r is strictly positive. And this guy over here is the multi-valued. And to deal with this guy, we had to use this branch cuts. And again, if you want to know which is the principal branch, as I discussed a few minutes earlier, this over here is our principal branch. So, and this will correspond to n equals to 0. So if you want to write the principal branch, it's often denoted as like this: principal branch for log z will be denoted as ln of r I the theta principal, that is n equals to 0 case. And your theta is restricted by what? Like this. Oops, there's a minus sign. Yeah. And there is also another condition. And what was that condition? That r should be strictly positive. So whenever you see something like this, you can easily tell that this is a principal branch. That is, you are evaluating log of z for any z inside this region. That is, okay, let me just highlight it again, inside this region. And you can choose another branches as well, and in the following videos we will see some examples. So this will be it for today, and thank you.